Yet another super professional video made by recording the screen with a camera, because screen recording software is not cooperating with the PDF format. AQA, some kind of organisation, I don't know who they are. Anyway, it's a GCSE Physics exam. This video not sponsored by Sam and Dan. Higher tier, paper 1, oh yes. They have a higher tier and a foundation tier of paper 1 and of paper 2. I'm assuming it's just two different papers in case they're being sat on two different dates. It's from 2018, so no, I'm not helping you pass this year's exam. This year's exam really happened. Well, I am, but I'm not providing the answers directly. You must have a ruler. Well, I have image editing software. Also, there's a steel ruler on the table behind me. A scientific calculator. I have a calculator app. The physics equation sheet enclosed, which I have not bothered to download and open. It probably tells you things like F equals ma. Use black ink or black ballpoint pen, not on my monitor you don't. Fill in the boxes at the top of this page. With like... yeah, you know, put your name on your work so they know whose it is. Answer all questions, that's nice to know. Not just, you know, every odd numbered question. You are expected to use a calculator where appropriate, and to abuse it where inappropriate, right? Reminded of the need for good English and clear presentation. Well, that's flat earthers shit out of luck, isn't it? Figure 1 shows a student walking on a carpet, on his or her toes with knees bent, wearing Christmas socks, because that's what students are like. A student becomes negatively charged because of the friction between his socks and, you're assuming a student's gender, and the carpet. Explain why the friction causes the student to become charged. Right, because the guy who originally discovered static charges first noticed the charge on the rod and called it positive, the charge is opposite to the distribution of electrons. If the student has a negative charge, that's because they have a surplus of electrons. A positive charge is a deficit of electrons. This wants 2 marks, so friction is resisting motion, therefore energy from motion is being lost. Some of that energy is going to displacing electrons from the material of the carpet to the student. And they're not immediately flowing right back because there isn't that much conductivity there, so they build up on the student. The student conducts pretty well, so they'll spread throughout the student. The student's head is represented by the sphere in figure 2, a perfectly spherical head. Wow. You guys got upset when we approximated the Earth shape to a sphere. The student is negatively charged. The arrow shows part of the electric field around the student's head. Draw 3 more arrows to complete the electric field pattern. I haven't checked the answers, and I'm a virologist, but this is only GCSE. I would draw arrows 1 each side and 1 down here, but you could get really cheeky and draw them as a tetrahedron, 1 here and 2 this side, with perspective on them. If you know what perspective is, flat earthers, shit out of luck, again. All pointing inwards. I'm hoping that's correct. The negatively charged student touches a metal tap and receives an electric shock. Explain why. The tap is part of the plumbing. If the building has been built and plumbed properly, it is earthed, and therefore it's neutral. Therefore the student has an electron surplus relative to that tap, and of course that static build-up while walking has put a positive charge, meaning an electron deficit, on the Earth in general. When the student touches this piece of metal, which extends in various forms a long way through the Earth, suddenly there's conduction. There is the ability for those electrons to flow from the student to the electron deficit of the Earth and neutralize that electrical charge difference. So they do. And that current causes muscles and nerves to fire. Sorry, it causes nerves to fire, which causes muscles to spasm and sensation to be felt, which is electric shock and associated twitch. Turn over. I want to turn over. I'd look silly standing on my head with my feet in the air. Next page. Some carpets have thin copper wires. See above. They conduct electricity. The student is less likely to receive an electric shock after walking on this type of carpet because every time the student touches a copper wire, the tiny charge that has built up since the previous time the student touched a copper wire gets earthed. And the currents involved are small enough not to qualify as electric shock. A teacher uses a Geiger-Müller tube because we don't trust students with Geiger-Müller tubes, they're fragile. And counter. The counter is quite important to measure the number of counts in 60 seconds for a radioactive rock. The counter recorded 819 counts in 60 seconds. The background radiation count rate was 0.3 counts per second. Calculate the count rate for the rock. Well, we have here count rate, and count rate is what we want. So I would assume that the units of the expressed count rate, counts per second, are the units they want. 819 counts in 60 seconds is, oh look, use a scientific calculator where appropriate. 819 divided by 60 is 13.65 counts per second. Background radiation was 0.3 counts per second. You subtract that 0.3 from the 13.65 registered, you get 13.35 counts per second. Include the units. Of course, I'm not sure I trust this answer entirely, because if the Geiger-Müller tube is close to the rock to pick up alpha particles which don't travel very far, the rock is shielding the Geiger-Müller tube from some of the background radiation. Potentially quite a lot of it. The background radiation was beta and gamma, not alpha, for the same reason, but the rock may well do a pretty good job of blocking beta radiation. Related question with related problem. A householder is worried about the radiation emitted by the granite worktop in his kitchen. A kilogram of granite has an activity of 1,250 becquerels. The kitchen worktop has a mass of 180 kilograms. Calculate the activity of the kitchen worktop in becquerels. 1,250 per kilogram times 180 kilograms is 225,000. That simple. 2 marks for that. Wow. Question 2 continues on the next page. Dun, dun, dun. Average total radiation dose per year in the UK is 2 millisieverts. We've changed unit from becquerel to millisievert. If you want to look the definition, why would I leave you to look them up? Let's go to Firefox, which I opened because I was hoping it would cooperate. I've forgotten how to spell becquerel. I was hoping it would cooperate with the oh no, I spelled it correctly, it just didn't come up as a search term. 1 disintegration per second is a becquerel, which doesn't actually tell you how much energy there is, because it could be coming out as alpha particle, beta electron, gamma ray, or a neutron. So, you know. Definition of... Well, actually, the definition of the millisievert is given in the question. I like the way it's all seconds. Oh no, there we go. Millisieverts. A radio protection unit measuring the radiation dose received either from a radioactive source, blah, 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 blah. Whole body effective dose. Thank you, that tells me exactly what it is. A seventh of a sievert. Marvellous, I could have guessed that much. Well, let's knock milli out of the definition and see what the definition of a sievert is. The search terms. The definition. Oh, great. To 1 gray or 100 rads. Definition of 1 rad. Definition of S1 rad. That's going to come up with something very weird. Definition of 1 rad. No, not 1 radian. Bloody hell. Pardon my French. Anyway, we have a table of how effective it is. It's quite possible the definition of a sievert is actually based on this table. You know, 1000, the middle row, radiation sickness unlikely to cause death. Maybe a sievert is simply the amount of radiation received that causes radiation sickness. Toxic dose 50 or some such. 10,000 immediate illness and death within a few weeks. That's what happens if you start juggling plutonium ingots. 100 is the lowest dose, TD low, the evidence of causing cancer. Okay. Average radiation dose from the granite worktop is 0.003 millisieverts per day, compared to 100. Explain why the householder should not be concerned about his yearly radiation dose. And by the way, 1 year is 365 days. I love this. They provide an insert with formulae, but 1 year is 365 days. Well, it's not. It's 365.25, approximately. It's not even exactly that. Anyway, if we have 0.003 millisieverts per day times 365 days per year times 80-year life expectancy of a human being, we get 87.6 millisieverts, which is less than 100 millisieverts, the lowest dose evidence of causing cancer. And if it doesn't cause cancer, it can't possibly cause any other harmful effects, so he's got nothing to worry about. Bananas are a source of background radiation. Yes, the banana is actually a unit of radiation. Banana equivalent dose, yes. One reason? Because people know full well that someone can eat bananas every day for their life and not turn into a giant tumour or Deathpool. Deadpool? Deadpool, isn't it? Deathpool is a Dirty Harry film. That might be a reason. Or because people know what a banana is, but nobody knows what a sievert is. They have to look it up and then they get stupid answers and definitions of radians instead. Be more aware of radiation risks, because it makes people more aware of the risk from eating bananas. Or because a radiation risk could be explained as a phenomenal number of bananas and people think you can't possibly eat that many bananas. I don't know. We shall see. There is a marking guide. A student investigated how the resistance of a piece of nickel-chrome alloy wire varies with length. What do we have here? We have a variable resistor, I believe, a switch, a battery, and a wire. Part of a circuit? That's a whole circuit. Also, there's something missing here. This should be an ammeter. But it looks like a variable resistor to me. Complete figure 3 by adding an ammeter and a voltmeter. Right, ammeter measures amps. It gives you an answer in amps. It measures the current, for which you want it connected in series. So I would remove this bit of wire here and put the ammeter in there in sequence, in series with the wire. And the voltmeter, you want it in parallel across the wire to measure the resistance drop, the voltage drop across that wire. Measure the voltage across the wire, which is how much the voltage from there to there drops because this wire is in the way. 3 marks for putting 2 meters into a circuit diagram. Okay. Data should include a risk assessment for one hazard in the investigation. Just one. C. Do not accidentally garrote yourself with the wire. Do not use 240 volt mains for this. Partly it's alternating current and would make a right mess of the project, and partly it would be likely to cause your instruments to catch fire. In fact, any high enough current, if you've got low enough resistance and high enough voltage, could cause part of that circuit to catch fire. If you know the voltage across your power source and the resistance of the variable resistor, that's kind of weird, you know, putting the variable resistor there. If you know the current flowing through it, voltage is current times resistance, so you could divide the known voltage from the power source I'm assuming this, oh, you need a minus symbol there. Assuming this is a, well, either you need a minus symbol here to complete it, or you don't need the plus symbol either, because that is always the plus side of a power source, but whatever. If you know the voltage across here, and the current that's running through, you know the resistance, total resistance of the entire circuit. You can then vary this and find out how much the resistance changes as you vary this. But what you're not finding out is the resistance of these wires here and the switch, the internal resistance of your power source, if that's batteries. With the voltmeter, you know how much current is flowing through the wire from the ammeter. And the voltmeter tells you how much voltage drop there is across the wire, so you know what voltage is driving what current through that much resistance. And you can twiddle this around to get various readings and plot them on a graph as current against voltage, and the gradient of the graph should be a straight line that you can then plot a best fit for all your results, which will, and the gradient of that line will tell you the resistance of that length of wire. Other problems. Chrome's toxic, so don't chew the wire. Wear insulating gloves. Disconnect the power source while assembling the circuit. Given that it's 2020 or 2021 now, disinfect all the equipment before and after use, just in case someone has coughed on it before use, and just in case you're infected after use. Is this enough for 6 marks? Why would switching off the circuit between readings have improved the accuracy of the student's investigation? Because the temperature changes. As I said, there's a risk of it bursting into flames if you put too much current through it. As wire gets hotter, its resistance increases. The charge flow through the wire, now that's a strange way of describing the electron current, would not change if you switch off the circuit. Well, that's bollocks. The potential difference of the battery would not increase. Why would the potential difference of a battery increase anyway, unless you're recharging it? The power output would not increase. The heck? The temperature of the wire would not change. There you go. But it would change. It'll cool down when it's switched off, and it'll heat back up when it's switched on. I'm still going for the temperature one, but it is going to change. Crocodile clip, jockey. Using the jockey allows you to contact on this point here, whereas the crocodile clip is attaching here and here. It's attaching at both sides with... Why are we getting mouse over? Blah. The jockey is attaching at more like a single point, so you can more accurately measure the length of the piece of wire that you're studying. Although the crocodile clip bites into the wire and might damage it. How would using the jockey have affected the accuracy and resolution of the student's results compared to using the accuracy of the student's results would be higher? Yes. And no, and no. Okay. The resolution of the length measurement would be higher. Yes, it has to be. That's why you get the higher accuracy. Next page. There are no questions printed on this page. Do not write on this page. Are we done? No, we're not done. Cyclist riding along a straight, level road at a constant speed. Straight and level, not flat. Chemical potential energy store in the cyclist's body decreases. Is speed of the cyclist is constant when the work done by the cyclist is blank the work done against air resistance. They probably mean equal to. But that's assuming that no work is done bending the tyres here and having them spring straight again here as they rotate, that no energy is lost in any of the bearings. And that the student breathing isn't affecting velocity. I mean, you suck air in from front of you and then blow air out in front of you, don't you? Well, unless you're sucking it up through your nose and blowing it out through your mouth, or sucking it in through your mouth and then blowing it down through your nose. But this is GCSE Physics and everything's an approximation. Yeah, that looks about right. Because air resistance is proportional to the square of the velocity, I would expect something like that. Write down the equation that links power, time and work done. Work done equals power times time. If we need to write down this equation, it must not be on the insert sheet with the equations on. Calculate the work done by the cyclist when his power output is 200 watts for 1,800 seconds. 200 times 1,800. But it's 200 watts times 1,800 seconds is 360 kilojoules. 3 marks. 3 marks? They even put the joules there. So it's not one for getting the units right. How is that worth 3 marks? Calculate the percentage increase in speed of the cyclist when the power output changes from 200 to 300. 50. 300 divided by 200 is 1.5. Minus 1 is 0.5. Multiplied by 100 is 50. 50%. The maximum, 300 is 150% of 200. The maximum speed the cyclist can travel on a level road is 14 meters per second. How does cycling uphill affect the maximum speed of this cyclist? It'll slow him down because he's having to put energy into increasing the gravitational potential energy of himself and the bicycle at a rate equal to his forward velocity multiplied by the tangent of the angle of that hill. And the rate at which energy is going to gravitational potential energy is a rate of work done, which is energy he can't use, work he can't do, overcoming air resistance. Displacing air, frankly. Choose answers from the box. To complete a sentence, the current through an ohmic conductor is directly proportional to the blank across the component, potential difference, provided that the blank remains constant. Power. Potential difference across the component provided that the power remains constant. The power being potential difference multiplied by current. There's a current potential difference graph for a filament lamp. The higher the voltage, the more current, but the hotter it gets, the more resistance, so the less the current increases. Oh look, I just explained that. I mean, if this was A-level, they'd want to actually know that the individual atoms of metal within the filament are bouncing around more, making the distances between them greater, making it harder for electrons to jump from one to another, for current to flow through it. Filament lamps are more energy efficient. It means you get more light and less heat per joule of electrical energy consumed. Or, yes, it does mean that. Or you consume less electrical energy for the same amount of light produced. A light-dependent resistor. Fixed resistor, 2000 ohms. Voltage running this way to outside lamp circuit. 2000 ohms here and variable resistance here will split this 12 volt potential difference from here to here in proportion to their resistances. So if that's 2000 and this is 2000, it'll be 6 volts across there and 6 volts across here, which is 6 volts going to the outside lamp circuit. If that's 2000 and this is 1000, it'll be 8 volts across here, 1000 across here, sorry, 4 volts across here. So only 4 volts to the outside lamp circuit. If this is 2000 and this is 6000, this is 1/4 of the total resistance. So 1/4 of the voltage here, 3 volts, and 9 volts across here going to the outside lamp circuit. Light intensity decreases. What happened to the potential difference across the LDR and the current in the LDR? The potential difference will increase and the current will decrease because the current is getting diverted this way. What is the resistance of the LDR when the potential difference across it is 4 volts? Well, the reason is pretty much as I already explained, that this voltage is split across these two in proportion to their resistances. If this is 4 volts, it is 1/3 of the 12 volts from there to there. So this must be 1/3 of the total resistance from there to there. So that must be 2/3, so that must be half of that. It is 1000 ohms. The resistance of the LDR is 5000 ohms. Give your answer to 2 significant figures. Woo! We are getting into advanced stuff after all. 2 sig figs. If the resistance of it is 5000, we have a total resistance of 7000. Because 5000 plus 2000 equals 7000. They probably want you to include that. Right, we have 12 volts and 7000 ohms. 12 volts, excuse me, divided by 7000 ohms is 0.0017 amps. Total current, but that's not going to be the answer. Because if we have 2 there and 5 there, we actually only have 5/7 of 12 up there. 5/7 is 60 over times 12, or 60/7 is 8.57 volts across this. 8.57 volts across it, 8.57 sum, 8.57143 if you want to be really fancy. Across 5000 ohms, we now divide that by 5000 ohms and we get 0.0017143 amps, but they want 2 sig figs, which is just 0.0017, or in scientific notation 1.7 times 10 to the negative 3. Or you could call it 1.7 milliamps. So they've already put in amps here, so 1.7 times 10 to the negative 3, or just 0.0017. Smoke alarms containing alpha radiation source, chucks out helium nuclei at high velocity, scary stuff. And a radiation detector. They're scary, but only if it gets inside you, because they can't go through skin or paper or like 5 centimeters of air. Figure 9 shows part of the inside of a smoke alarm. For radiation, smoke particle radiation. Big surprise. Yeah, not at all. Because the smoke particles block the alpha radiation particles. Because they can only go through 5 centimeters, not going to get out of the thing into you. They can't get through your skin, they can't get through air, they just turn into helium. They just steal electrons from other stuff they hit and turn into helium. And this video is about to reach 29 minutes and stop.